we'll discuss uh, homotopy. Homotopy. So intuitively, homotopy of maps between two maps is a continuous family of maps from starting from one map to another, ending at another map. F from X to Y, then G from X to Y. So homotopy is this family of maps formal definition. Before we write formal definition, first we'll establish some notations. A topological pair, topological pair is XA consists of a topological space X and a subspace A of X. If A is empty, denoted by this, then X Y is identified with X, right? We will not differentiate between X between this pair and this topological space. So we'll consider this topological space and this topological pair and this topological space X as same. A subpair pair X prime A prime is a pair such that X prime is subspace of X and A prime is of A. A continuous function f from X to Y such that FA, FB is called a map F from right? In particular, if A is in T and B is in T, right? Then what is a map from X C to Y C, right? So this X P be denoted by X itself, Y P by Y. So a map from X to Y is what? Just a continuous function from X to Y. But previously, you might not have been uh, differentiating between map, mapping, or function, right? You used to say that they are same, right? But here, this kind of convention will be using. Uh, so if there is written somewhere that if map is written somewhere, you further by that you consider continuous function, right? So map here will be considered as continuous function. So when I say that f from x to y is a map between topological spaces x and y, that means that f is a continuous function. Is a map. It means f is continuous. Next, there is a category. There is a category of topological pairs and maps between them, right? So in that category, topological pairs will be objects and maps between topological pairs will be morphisms. The category of uh, topological spaces and continuous functions is a full subcategory of this category. You see that given a topological space X, we can identify it with this, right? So this, of course, it is an object in the category of topological pairs and continuous functions. So these kind of things, they are object there, right? And of course, home X, Y. So this is nothing but home X comma phi, Y comma phi, right? And this is what? Uh, this is a morphism set from the object X phi to Y phi. So this is, so hence this category of continuous topological spaces and continuous functions is a full subcategory because of this. Similarly, the category of uh, pointed topological spaces and continuous functions is a full subcategory of the category of topological pairs and maps between them. Next, uh, some more notations. We denote the pair x cross I cross I by xa, just for simplicity. What is this? I is simply this closed interval 0, 1. So let us see the definition of homotopy. So let x prime be a subspace of x and f naught m1 f1 from x to y be maps, means continuous functions. So usually I will not repeat, I will just say maps. So for that you should consider that it is continuous function. So these are maps which agree on x prime. That is uh, f naught x equal to f1 x for every x in x prime. Now uh, we say that f naught is homotopic topic to f1 relative to x prime denoted by this is homotopic to f1 relative to x prime. So this is the notation. So it is called f naught is said to be homotopic to f1 relative to x prime if there exists a map uh, capital F from xa cross I to y. So what is this? You can just see here. It is this, such that f of x 0 is f naught, f of x1 x comma 1 is f1 x, x for every x belonging to capital X, and f of xt equal to f naught x equal to f1 x for every x belonging to x prime and t belonging to I. So this is the definition of homotopic maps. So after we see some examples and things will be more clear. And this map, uh, such a map F is called homotopy topy, relative to x prime from f naught to f1, and is denoted by f from f naught f1 relative to x prime. If if uh, x prime is empty, we don't use the phrase relative to. So clearly uh, f naught is homotopic to f1 relative to x prime implies uh, f naught is homotopic to f1 relative to x double prime if x double prime is subset of x prime. A map f from x to y is said to be null homotopic if it is homotopic to some constant map. Homotopic to some constant map. Uh, to make you understand the things till bit, before we start giving examples, you just see that if uh, we consider maps f naught f1 from x to y. In place of x, if we consider I itself, right? Then what will be then f will be from I cross I to y. So here your A and B, we are taking as empty set, right? And if we consider your x prime to be the subset of I, x, that is I, just 0, 1, then what will happen? What is I cross I? I cross I, you can consider this as this this square, right? So, so this is what this is. It is basically uh, I cross 1. This is your I cross 0, right? So when f is restricted over I cross 0, this is going to be f naught, and when f restricted over so this is f is from here to y. So when f restricted over uh, this is basically f naught. When it is restricted over this one, it is f1, right? In between, so uh, and here, right? So at all these points, this capital F is constant. See, similarly, at all these points, capital F has same value, right? So basically, F uh, 0 t equal to F t uh, sorry F0 0 equal to F1 0. Similarly, F1 t equal to F0 1 equal to F1 1. So this will give you some intuitive idea. So for t belonging to I, define ht from xa to xa cross I by ht x equal to xt. Now, if f from f naught to f1 is homotopy relative to x prime, then this h naught equal to f naught f h1 equal to f1 and f h t restricted over x prime equal to f naught restricted over x prime equal to f1 restricted over x prime. For every for all t belonging to I. So you can see that this ht this thus fht is it is a one parameter family of maps is a one parameter family of maps from xa to yb agreeing, so those maps they agree on x prime and connecting f naught equal to f h naught and this connecting this to f1 equal to fh1. And this with respect to so what let us discuss a little bit more. So this fh we can consider it to be a map from I to yb a which agree yeah. So yes. So what is this? You might have seen some place at some places when I say that r is square. What is this meaning? Basically, this is r 1, 2. You can realize it like this, right? Collection of all this denotes collection of all maps from 1, 2 to r. So if I write x, y, so this is collection of all functions from y to x. So here this will denote a collection of that set of all maps from xa to yb. Uh, uh, yes, collection of all maps from xa to yb. In our case, uh, because it is relative, so we can consider this to be collection of all maps from xa to yb which agree on x prime. right? Now, how we'll define this map? So f at t is nothing but f at t here. This at t. So we can this is a set. We can put a topology on it. Uh, so we can put a topology. That topology is called. I mean, of course, we can put so many topologies, but for our purpose, we can put compact open topology. Compact open topology. So what is a compact open topology? Uh, it is a topology generated by this is compact in X, U is open in Y. And what is this pair? So uh, X A this pair CD, meaning of this CD is CD is collects all maps F from, so C is subset of X, D is subset of Y. So this CD means all maps from X to Y such that FC takes FC is contained in D. So this KU is collection of all maps from K to U, so from X to Y, such that FK is contained in U. And additional condition here is this is the collection of those pairs KU. What is KU? It is defined from like this, uh, such that K is compact and in X and U is open in Y. If you consider this collection, this is a sub collection, this is a subset of this, right? So if you consider this collection as sub basis, then it is going to give a topology, right? Uh, whose sub basis is yeah. So by taking this collection, right, you can generate a topology of which this collection will be a sub basis, right? So how will you generate that? There is a familiar method. So you will consider all finite intersections over this collection, and then whatever you will get, you will consider all arbitrary unions. Then what you will get, that will be a topology. So that I hope that you have already studied these things in your the general topology course. It is expected that you have already studied these things. So with respect to that topology over this this map, right? Basically, you can consider this map to be a one parameter family of maps from XA to YB. Uh, so this will be continuous. So this function fh from I to this, which is basically this one parameter family of maps from XA to YB with this property. So this fh is going to be continuous. So if you take compact open topology over this. So that is why, so given any homotopy F, we can have this continuous family of maps with respect to suitable topology on this. So this is called, so with that, this is a continuous one parameter family. That is why we say that a homotopy is a continuous family of maps.